Okay, nice to see you. I'll talk about the lunar sodium exosphere and its tail based on three-dimensional Monte Carlo simulations. And this presentation is based on my recently published paper in GGR. And this work is collaboration with several scientists in Kyung University, South Korea. Okay, I'll present in this order. So the lunar exosphere, as you may know, exosphere means a transition area between atmosphere and interplanetary space. Actually, lunar regolith contains many different species like this, but lunar sodium exosphere is well known so far. Why? Because the sodium has a good reflectivity compared to the other materials, so it's easier to observe, so well studied so far. And for the case of the moon, this part of atmosphere is totally missing, so lunar exosphere is bound at the lunar surface. And here are several sodium exospheres observed in our solar system. This is for the moon and the Mercury and Io cases, and this is a lunar horizontal glow due to the lunar dust. And there have been many previous studies for the lunar exosphere. After the first discovery of lunar exospheric sodium and potassium by Porter and Morgan in 1988, many theoretical and observational efforts have been made. Among them, we focus on the Flynn and Mendelow's imaging data for the lunar sodium coma, and we also try to explain the first spectrum of the lunar tail observed by Mirkiewicz et al. So, as you may know, the lunar exosphere could be generated by the continuous bombardment of solar activities like solar radiation and wind and summer desertions, and otherwise isotropic bombardment by micrometeors on the lunar surface. So such sputtering process can form a neutral sodium corona, which is being seen by resonant scattering with solar radiations. And there are three major loss mechanisms for the lunar sodiums. Unfortunately, so far there are only a few published sodium images in literatures. And this comes from Flynn and Mendelow and Porter and Morgan. And these two images obtained by coronagraphic observations. Actually, this Flynn and Mendelow's first coronagraphic image is very valuable for us. We can see that there is a little bit of asymmetry between the east and the west side. We carefully extracted this 5 range of discrete brightness scale by using a digitized scanner, and we tried to model this 3-dimensional brightness scale through the modeling. So here is some features of our simulation code which can simulate lunar coma and the tail. And this is particle simulation with Monte Carlo techniques, including all major gravity sources and major 3 loss mechanisms also. And it also include umbra shielding effect of the moon and even the Earth. And it can be applicable to any geometry of the lunar faces. One distinctive feature of my simulation is that it considered simultaneously the day size source and the isotropic source both together, and tried to adjust the free parameters to reproduce the observational data. So by using this code, we made a systematic investigation for the 2 important observational constraints. The first one is 3D brightness distribution around the lunar limb, and the second one is receding velocity distributions of the tail. So here is a brief comparison of my simulation with previous simulations, and we actually made a wide range of free parameter space searchings. And here is a snapshot of my simulation. We can see that day size source is happening on the green area, and isotropic bombardment by the micrometeors happening on the whole 3D lunar surfaces. And this blue and red dot represent their receding or approaching velocities. This is for the case of first quarter. And here is the previous two-dimensional radial profile analysis by Flynn and Mendelov. In this case, there is some discrepancy in the radial brightness modeling with their observation. We can see some discrepancies here. And in our cases, we made the same two-dimensional analysis based on our modeling, and we found very similar conclusion like the previous authors. Yeah. In this case, this left panel represent the day side dominant case, and this right side panels represent isotropic source dominant cases. In this case, we also found very similar conclusion like the previous authors, in which the day side source is dominant with very narrow Doppler width is applied. However, during our three-dimensional analysis, we found the opposite result. Here is our best Coma model for the lunar exosphere, sodium exosphere. Here is the brightness map around the lunar rim. This is for the third quarter phase, as the same with Flynn and Mendelov's data. And we can see the umbra shielding effect of the moon and so on. So here is the best three-dimensional model which can explain all the observed brightness scale by Flynn and Mendelov. This thick line represents our simulated brightness scale, which corresponding each observed brightness scale represented by the color symbols. And the lower graph shows our theoretical expectation for the brightness variation with solar zenith angle as a function of different lunar radii. And here is a comparison for the two opposite contribution ratio. The upper graph is the case for the isotropic dominant case, and the lower graph is day-side dominant case. We can see that the upper case shows much better fit to the observational data. And we also simulated lunar sodium tails, which looks like a cometary tail if we see above the ecliptic plane. Actually, the lunar sodium can fly over beyond the Earth's orbit. During a new moon phase, we can observe such a lunar sodium tail, which is the so-called lunar sodium spot. This is due to the gravitational focusing effect of the Earth. And its spectrum was firstly observed by Miarkiewicz et al. Recently, and the peak velocity was about 12 kilometers per second, and its Doppler width is as wide as 7 kilometers per second. And please note the widened features toward the higher velocities. And here is animation for the lunar sodium tail with a different lunar date before and after the new moon phase. We can see such a streak getting concentrated on the anti-lunar point, and the morphology is completely reversed before and after the new moon day. And here is our simulated morphology depending on each lunar day. And the lower graph shows the corresponding receding velocity distribution. In this case, we adopt a variable radiation pressure effect. Then we can obtain such a higher receding velocity and widened feature toward the higher velocities. And this lunar sodium tails morphology is also depending on the initial model parameters. And here is a comparison between the constant radiation pressure The upper graph shows the constant radiation pressure case, and the lower graph shows the variable radiation pressure case. So if we just assume the constant radiation pressure effect, then we only can achieve the peak velocity of 6 or 7 kilometers. But once variable radiation pressure is applied, then we can easily obtain such higher peaks and widen feature toward the higher velocities. So from the lunar Coma data analysis, we found that the best contribution ratio between isotropic and day-size sodium is about 70% to 30%. So isotropic source is dominant, and the estimated velocity factor between the isotropic and day-size sodium is about half. And the total production rate of the sodium from the lunar surface is about 0.7, 10 to the 22 atoms per second, and which is very consistent with the Wilson et al. Result. And also, based on our best 3D Coma model, which actually has a very narrow Doppler width, we can coherently explain the observed high and widened spectrum as well. And so far in the literatures, people have adopted various values for the photoionization time of sodium. So it may be necessary to study further about the appropriate value around 1A orbit from the sun. And in Kyung University, we are going to accumulate more observational data for the lunar sodium corona. So we developed this lunar corona graph recently and tried to make more observation for the future modeling. And this is the first light of Gyeonggi lunar corona graph, and this is the size of the corona mask attenuating the orbit of the moon. So here is our future plan. So we need to make more monitoring observation to accumulate more data to see any phasal variation and long-term variations, and to provide more observational constraint for the future modeling. Okay, thank you very much.
Thank you very much. We do have a question.
On the coronagraph that you are working on, I assume you're using a narrowband sodium filter.
Yes.
What is the bandwidth of your filter?
It's about 15 angstrom.
15 angstrom.
Yeah, yeah.
Thank you.
Yes.
Hi, I just want to. Oh, okay. I just want to invite everybody to our poster. It's E13, and we've also simulated the lunar exosphere, but we've simulated sodium, potassium, magnesium, and calcium. And our goal was to look at the effect of a coronal mass ejection passing the moon to see what the effect of ion sputtering, and we considered that the remarkable thing about sputtering and a coronal mass ejection is that the composition of the solar wind during a coronal mass ejection is actually very highly enriched in helium double plus and heavy highly charged ions, and so the simulations that we've shown are also 3D Monte Carlo simulations, and I have some movies, but unfortunately I can't show them in the poster, but the effects are actually quite dramatic, and I urge you to come by the poster. It's E13. Thank you.
Thank you. Any more questions? All right. Thank you. We should thank our speaker.